All right, so the Carnot cycle. So, like I said, this is like the pinnacle of thermodynamics, and it's like almost a secret password. So you will know if you run into another chemist and like you ask about classic problems. I know this is a great dinner conversation. What are some classic problems you did in your curriculum? The Carnot cycle will be one of them. Take the subject exam for the GRE. There'll probably be something related to the Carnot cycle. It won't probably be all of the extensive calculations we do today. It'll probably be the Carnot efficiency, which all you need is the hot and cold temperature, and you can tell the efficiency of the engine. So that's part of the reason why we love this cycle. There's some really simple pieces to it, and then you can take any kind of engine and break it into little bitty Carnot cycles. So you can use it almost like an engineering finite element analysis tool. So in finite element analysis, you take any large object and break it into smaller pieces, and you model the stress and strain on each one of those little blocks, and then you add them all together to get the stress and strain on the whole object, and you can determine where it's going to fail. In this case, you take a really complex cycle and break it into little tiny Carnot cycles, and you could model the overall efficiency of a real engine. So this combines several of the things that we've done so far. Get over here and click that one. So it combines the isothermal expansions. Can I get you to hit the middle switch? It cuts these lights here and makes it a little easier to see. Yeah, perfect. So it combines the isothermal and adiabatic expansions and compressions into a cycle. So we have this expansion here. You see the little arrows. So we go from point A to B. That's the first leg. B to C is adiabatic expansion. See how it's steeper than the first leg? So the first leg is isothermal, then adiabatic, and then we have a compression. We're now at the cold temperature. So the temperature drops when we do the adiabatic expansion because we're expanding, but there's no heat flow. So something has to give. We're not putting heat into the system anymore. We're just expanding, so the temperature drops. Then we're at the cold temperature. We do an isothermal compression to reset the system to point D, and then an adiabatic compression to reset it all the way back to A. So we do the compression on the cold side where it's easier to compress. Look at the pressures. The pressure is the y-axis. So pushing against a cold gas is easier than pushing against a hot gas. The colder the cold gas, the easier it is to compress, the more efficient the engine is, because that's where we're putting in work into the system. When we compress that gas, we're putting work into the system, and we're getting it back to point A. The last adiabatic compression raises the temperature up to the hot temperature at point A. So here are the equations and the assumption, or the facts, I would say. For isothermal expansion, delta T is 0, so therefore the internal energy change is 0, and so the heat is equal to the opposite sign of the work, and the work is given by this isothermal expansion equation with VB over VA. And the hot temperature. So these are the 2 places or 3 places you can go wrong. You can get the wrong volumes, you could have it upside down, and you could have the wrong temperature. And so we can go through and we can label these things like this, just to make sure that we're clear. Since this dark line's an isotherm right here, that's T hot, and this is T cold. And you see how they're the isothermal slopes, and then the adiabatic slopes are steeper. And the steepness of those adiabats depends upon the type of gas, whether it's a monatomic gas, a linear gas, or a nonlinear gas. Then we have the adiabatic expansion. For the adiabatic expansion, it's adiabatic, so the heat change for BC is 0. Therefore, the work is equal to the change in internal energy, and that's just a function of temperature. So here we have that heat capacity at constant volume, which again depends upon that substance, the heat capacity of the working gas, and it's cold minus hot. That's a place where people mess up. They always take the big versus minus the small, and it should be cold minus hot. So this should be negative. So that's a place to catch yourself. Both of these works on the top and the bottom are negative. Okay, because energy is flowing out of the system to the surroundings. So we're doing work on the surroundings on those expansions. We're pushing that piston, turning a crank, doing work. Then when we compress at the isothermal on the cold isotherm, we put heat into the system and we do work on the system. So the work is positive because we're compressing it. We're compressing, we're taking the heat out in that step. And then over here, we're doing work on the system as well. So we're putting work in. I'll change this to a W here. So this looks like it would be a negative value, but it's not because this is less than 1. And this one, the hot minus cold, that's a positive number. So this right here is also going to be positive work. So we'll have a couple of negative works and a couple of positive works. We can take all of those, add them together, take the absolute value, so we get rid of the sign at the end, and then we divide it by the heat that we put in on leg AB. So this is in the Carnot cycle, that's the only positive heat value. And that's the heat we paid for. That's the energy that we put into the system to get this thing to go. So when we're doing that isothermal expansion, we're getting work out, but we're putting in heat to maintain that hot temperature. And then the rest of the ones, either heat is 0 or heat is negative. And then the efficiency, that's the efficiency using work and heat. There's also a different efficiency over here that E is equal to 1 minus TC over TH. And so there's a great way to check your work at the end. So when you get finished with all of this and you have all your work values and your heat in, you can calculate the efficiency and then you can check it with your math using just the temperatures. Now, all of these temperatures are in Kelvin. So okay. And this is the one that catches people. I think in one of the homework problems, and often on the test, I'll give you temperatures in degrees C. And so you're looking at the efficiency and you say, why isn't this engine, like if I gave you the cold temperature of 0 degrees C and the hot temperature 100 degrees C, okay, then it would look like a perfectly efficient engine, okay, because your TC was 0. And so you circle 100%, and that's wrong. Right, so you're not going to have a 100% engine either, because that should tickle your something's wrong button. Okay, and so you convert it to Kelvin, and it's really 273 over 373. Okay? Hardly 0. So let's actually use our little Toyota engine simulator that we had. These are all of the values for like a Toyota. I forget what model it was, but I put it in the other day. So let's use these values. These are slightly different than the ones on the homework. You have the little Trans Am calculator. That site has disappeared, so I went and tried to click that link, and it's defunct. So I searched for another one. I found this one. And so let's use this compression ratio and this cylinder volume here. So this is going to be our cylinder volume, 0.415 liters. times 6. So we're going to do that times 6. So we have our compression ratio and our delta V and so on. So let's calculate VA. Let's see. So what is 6 times 415? 2.4 what?
2,490.
So we'll say 2.49 liters. That's our delta V. So that's 2.490 liters over 9.03 minus 1. So if someone with a calculator punch that in. So that's VA. See here? So that's our smallest volume. In the Carnot cycle, that's VA, real tiny volume. Now let's do VC. So now that we have VA, we can put it in that other equation. So we have 0.31 liters times 9.03. Oops. You get 2.8 liters.
Yeah.
Okay, great. Now, a lot of times we have, temperatures in Fahrenheit. So if you look at your dashboard and you see that the cold temperature, the radiator temperature is at 210 Fahrenheit, let's calculate that in Kelvin. So this is a good review of how to calculate that in Kelvin. So we have, in parentheses, 210 minus 32 degrees Fahrenheit. And then, do you remember the conversion factor for that? If you can't remember it, think about water boiling. Okay, so what's the range of degrees of Fahrenheit for water boiling? It would be 212 minus 32. So 212 minus 32 is 180 degrees between boiling and freezing. Okay, does that make sense? What about Celsius? It's 100 degrees. So 100 over 180 is the conversion factor. So you can always remember that if you remember water. Water for Celsius has 100 degree units. Water for Fahrenheit has 180 degrees in that same distance between boiling and freezing. So you know those have to be the same temperature. Boiling is boiling no matter what degree scale, and freezing is freezing. So on top we have 100 degrees C, bottom is 180, or it ends up being 5/9. So that's the least common multiple of all of those. Okay. So 5/9. So it's 5 degrees C for every 9 degrees Fahrenheit. And then that gets us to degrees C. And so then we add 273 to it. What we're missing here is just a 1-to-1 conversion where we convert degree C to Kelvin, and it's 1 Kelvin for every 1 degree C. So that's why we can add Kelvin directly to degree C, because it's the same unit increment. So that's going to give us the temperature in Kelvin, which looks like it should be, let's see, we're doing the cold one. Or I've got that backwards, don't I? I have hot and cold. So this is cold. This is hot. Okay. So the cold is 372. Is that what you get? 372? Kelvin. And then the hot, oh, that was okay. Gosh. And then the hot was 923. So let me just show you that. 1200 degrees F. I'm going to show you explicitly minus 32 degrees F. So that tells you how far it is above boiling. This converts it from 5 degrees C for 9 degrees F. And then I'll show you that one that I left out before. So then it's 1 degree C for every Kelvin. So that's a conversion over to Kelvin plus 273 Kelvin. That way you're not bothered emotionally by adding Kelvin to Celsius. Okay. And so that's where we get the 923. Now this 0.08 moles of gas, that's a guess. I went through and I calculated what the gas mileage was. So that's say 20 miles per gallon. So that's how many gallons you use in 20 miles. Going 70, right? So that's 70 miles per hour. So now I have gallons per hour. Okay. And then that's roughly running at 2,000 rotations per minute. So I calculated gallons per minute. That's how many rotations of 2.5 liters per minute, per hour, per 20 gallons, per 70 miles. And so I parsed it all the way down, and it's like 0.05 to 0.08 moles of gas is being consumed, okay, every cycle. So that, I'm not sure that's perfect, but it's close. That's where that number came from, is I just took, 70 miles an hour, 20 miles per gallon, worked it out in terms of how much fuel was being consumed. I even got into moles of the fuel and put it in that was 0.08 moles of gas. Now for our adiabatic relationships, let's just use a monatomic gas as a working fluid. We can try to figure out maybe they should be linear, maybe it should be CO2, and what do you do with water? Water's bent. So what ratio of exhaust gases? That gets all really complicated. You're making a lot of assumptions. So let's just go with a monatomic gas as a working fluid. And so then how much work is produced and how much heat is consumed and what's the efficiency computed both ways. So this is the kind of thing where given these values, we can answer all of these answers. Okay, so let's go into it. So here's our state variables table. Remember, we know T hot and T cold. This was 210 degrees Fahrenheit, and this was 1200 degrees Fahrenheit, which we converted over to Kelvin. Okay, and the Kelvin was 372. Notice that once I find T cold, I write it twice. I put it in 2 rows. I put it on row C and row D, and then up here I have 922. Okay. So that's pretty easy. I've got my temperatures, and then I've got my volumes. So volume A was 0.31 liters. And volume C was 2.8 liters. And with that information now, I can calculate everything else. I do have to assume the working fluid to get gamma. Because remember, gamma is Cp over Cv, so we've got to figure out what that is. So let's go ahead and calculate that. Gamma, we'll go over here. So let's do Cv for a monatomic gas. Okay, so what is that? This goes back to exam 1. Pardon? Yeah, you're calculating the whole thing. So just the CV is 3 halves R, right? So 3 halves, there's only 3 halves because a monatomic gas can only translate. And so then we add another unit of R to that for CP. And so up here is 5/2 R. And so the R's cancel, 2's cancel. And so that's equal to 5/3, or 1 2/3, or 1.66. So that's gamma. So 1 over gamma minus 1 So let's see, 1 over 5/3 minus 3/3. So 1 over 2/3 or 3/2. So that's going to be, this right here is going to be raised to the 3/2 power, and this will be raised to the 3/2 power. Is that right? Did I do it right? Always check my work. If you catch a mistake, I'm happy. I'm not upset. So now we can use our temperatures and our volume A and volume B, and we can calculate our other volumes. So let's do volume B over here. So we're looking for this volume here. This is B. This is A. And this is C. So we're looking at this. Which one of these lines is an adiabat? It's this one, right? So we're connecting B to volume C. So we use volume C to calculate this piece. And that's the thing, a lot of people mess up. They'll use volume A. So that's equal to 2.8 liters. And then we have TC, which is the cold temperature, 372. Over 922 Kelvin, raised to the 3/2 power. All right, so someone punch that in for me. Good, 172. Oops, something happened. Okay. All right, so that's VB. Let's do the same thing for VD. And here's D. And it's connected to A by an adiabat. So we use VA to calculate this one. So VA was 0.31 liters. And so the reason I'm making such a big deal out of this is because units won't help you if you get the wrong volume. It's still liters. And so you have to know how to set the table up and which volumes to use to calculate your other volumes. And so then now we're dealing with TC, or the TA over TD. So the hot over the cold. Okay, so this one will give us what volume? 1.21. So this is 1.21 liters. Now that we have, again, we have 3 out of our 4 variables. We have the number of moles of gas, so we know those. We have the temperatures in all 4 cases, and we have all 4 volumes. So with all of those numbers, we can calculate the pressures. And we get all of those pressures. It turns out, for the rest of the calculations, we really don't need the pressures, but to fill out the state variables table, it's good to calculate them. But can I just write them down, since this is straightforward? We just have nRT over V. We can write out those pressures. So the pressures the top pressure, PA, is 19.5 atmospheres. PB is 8.4. PC is 0.87. And then PD is 2.02. Thanks for letting me speed things up. What was your question? Okay, I know I told you the charts would be accurate. Okay, and I changed all this morning, and I pasted the accurate chart on the next slide. So I didn't realize that this one was still in there. Okay, so you're right to catch that. Let's go ahead and I'm going to go ahead and write these out here. VA was 0.31 liters. VB was 0.72. VC was 2.8. And VD was 1.21. Colon was 322. 372. And 922, right? I don't know if those are accurate temperatures. Like I said, they fluctuate. You step on the gas, you put more gas in, and the temperature shoots up. The temperature cold should not shoot up that much. Okay, so then the pressures, let's go ahead, 19.5. Eight 8.4. 0.87. And 2.02. So, if you were to calculate this and you had an accurate chart like you have here, you can check your work. Yeah, this looks like it's less than 1, 0.87. VD is around 2. That's good. VB is a little over 8, 8.4. And then VA is very close to 20. So that's nice. I'm saying V, but I'm talking about pressure. Sorry. So those are all the pressures. The volumes, this makes sense. The largest one is 2.8. Here's 2.53. Yeah, so that's about right. Then BD is about halfway, or 1.2. That's good. BA is down less than 0.5. So, yeah, it's 0.3. And then VB is less than 1. So it's about 0.72. So, yeah, they check out. Even if you didn't have an accurate chart, look at the volumes. They have to make sense in the sense that VA and VC. VA is always your smallest. So I will write that. Always. And always largest. Okay, and so then if that's the smallest volume, then this is going to be always the largest pressure. Does that make intuitive sense? The smallest volume has the highest pressure, and vice versa. So these are the state variables for the Carnot cycle. Now that we have these, we can do the work equation and the energy equations and calculate all of the thermodynamic values. So let's do those next. So here we are with our isothermal expansion. We've got all these, recognition of all of these facts for the isothermal expansion, and so we can calculate the work. And did I say 0.05 or 0.08 moles? All right, so which temperature do we use? We use the hot temperature. This is AB, leg AB is on the hot isotherm. It's 922 Kelvin. And then we have VB over VA. So final minus initial, we're going to B from A. So A is initial, B is final. So VB is 0.72 over 0.31. Okay, is it positive or negative?
Negative.
Yeah, so negative 517 joules. So the moles have canceled, the kelvins canceled, the liters have canceled inside the log, and so the thing we're left with is joules. So that's good. All right, so that's negative work. The system did. I mean, the system did work on the surroundings, so it lost energy in terms of work. Now up here, the heat is the minus sign of the work, so this is equal to minus 517 joules. So it's equal to positive 517 joules. Make sense? That's the isothermal expansion. Now let's do the adiabatic expansion. So here now we're going from the hot reservoir to cold, so it's T final minus T initial. So 0.08 moles times 8.314. Oh wait, CV. We need. We're doing a monatomic gas, and so we have 3 halves here times R. So this one gives us a similar number, right? So this is, again, a smaller number, 372 minus 922. That's going to give us a negative value. So this should be negative 549. Okay. And that's the work. So that's how much work comes out. Heat is 0. So the heat for this leg is 0 because it's adiabatic. So we only get work out of the adiabatic expansions. They're great. We like those. And you can imagine that's why the difference in temperature, hot and cold temperature, is really related to efficiency, because the adiabatic expansion is the thing that's really given us something for nothing, if you will. We're not putting heat in, we're just getting work out. So if we could really increase that adiabatic leg by separating our hot and cold temperatures, we really increase the efficiency. We get more work out of the system. Okay, so then this is just the same calculations, but with different values. Minus 0.08 moles times 8.314 joules per mole Kelvin. Now it's the cold temperature, 372 Kelvin. And now we have VD over VC. So VD 1.21 liters, 2.8. Is that right? Do I have them flipped? VD and VC? 1.2, 2.8, okay. Yeah, that's right. So this is less than 1. So that means this is going to be negative, and that's going to cancel this negative sign, so we have a positive work. We're compressing it, so it should be positive. So do you see how even before I do the calculations, I'm trying to analyze, is this going to be a positive result or a negative result? If I'm compressing the system, I'm doing work on it. So from the perspective of the system, the energy went up. I need to have a positive work value if I'm compressing the system. The system is that working gas inside the piston. So if I compress the system, work better be positive. Does everybody understand the signs? And if you don't have a positive sign, then something's wrong. That means you probably flipped the volumes or something, or you just forgot the one over there. Okay, so what does this one end up being? 280?
208.
208. Okay, this is isothermal, and so the heat is equal to the minus work, so it's equal to minus 208 joules. And we had to take that out of the system to keep it isothermal. So we compress the system, positive work, we're working on the fluid. When I say fluid, I mean the working gas. And in order to keep it isothermal, it would heat up if we just pushed on it. That would be an adiabat. But if we want to keep it isothermal, we have to suck that heat out. That's the radiator in your car. We're compressing that, we're pulling the heat out as we compress that gas, and we're keeping it at that cold temperature as long as we can. That last little bit, I tend to think of it as going too fast for the heat to flow out, and so then it jumps up to the hot temperature. Now in a real engine, we hit the spark and burn everything. Okay, but in this ideal case, we're just using compression to do it. Okay, and so then down here, the last one is the dA leg, so that's equal to 0.08 moles times 3 halves times 8.314. It'd be real easy to forget that 3 halves, wouldn't it? There's no units involved. It'd be easy to get it wrong too. So you got to know what assumptions you're making in terms of the gas. And this is hot minus cold, so 922 minus 372 Kelvin. Probably it should be 549. How did I know it was going to be the equal and opposite sign of 549? These are both adiabatic expansions, and they connect the same temperatures. So if I expand and go from a hot temperature to cold temperature, I get out 549. It's exactly the same calculation if I flop the temperatures. I'm just going up from the cold temperature to the hot. I've got a new final temperature, new initial temperature. And so these are going to be equal and opposite signs. And then this is adiabatic, so the heat flow for this one is 0. So we've done the heat and work for every leg. So the work for AB, okay, is minus 517. The work for BC is minus 549. The work for CD is 208. And the work for DA is 549. So we add all of these works together. Notice the 549s cancel. So in terms of the net work out of this thing, the adiabats kind of cancel out. It's isotherm at the top minus the isotherm at the bottom. So it's the difference between how much work you get at a hot temperature expanding minus the cold temperature compression. And then we divide that by the heat of AB. The heat of AB is our positive work, that's 517. These are all the terms. So what do we get for this? 0.6. Yeah, okay. I'll say 0.60. Pretty darn good. Okay, now it's probably, I don't know why it's so good. It shouldn't be that good. It's probably an assumption in either my temperatures are too far apart, which makes it way more efficient than it is, or I'm trying to think if it would matter how many moles of gas I have in there.
I think your revs might have been a little bit low. I think your rotations for 70 miles an hour. I think you had it at 2,000.
Yeah, but you know, like I've got an 8-speed transmission. You know, it's cruising pretty well at 2,000 RPMs. It can. Yeah, yeah, it makes a difference in terms of how many, you know, what kind of volume your pistons have and so on. Yeah. The Ford transmissions now are 10 speeds. So
that could be seen as like 60% efficiency.
Yeah.
So 60% of the energy that's in the gas is being converted to work.
Yes, yes. Which is not realistic really for a gasoline engine. I think they run around 25% tops. And diesel is 35%. So diesel is more efficient, and we'll see why. We'll look at the actual cycles, the diesel cycle and the gas cycle in a future set of notes, probably next time. So just some review slides that are there in your notes, just talking about concepts of these. You could use the temperatures to get the efficiency as well. And then if you have any actual cycle with lots of Carnot cycles, you could break it into Carnot cycles and calculate the efficiency that way. And here's the answer key. So it's on the video if you wanted to check your work, but we already checked our work together. But I wanted to make sure it's on the video. So great day. We did a lot of calculations today. Next time we'll talk about actual engines.